Hello, Tim Lyons here. I'll be presenting today's lesson today for Mike, who was unable to attend. He asked me to do it. I'm actually an engineer, well, he always calls me an engineer. I'm not technically an engineer. I'm just an employee here at Mind's Eye. I basically get to play with toys all day, so it's a lot of fun. So today we'll be talking about force, motion, and inertia. Yeah. So in the Mind's Eye Foundation education, we cover different units. The first unit we talked about introduction, the next continuous learning and improvement, the second applied systems thinking, variable force and motion, electrical engineering, and energy transfer. This is kind of just an overview page of the different types of units we'll be covering. Hopefully you can remember those units that we covered in the past and be able to look forward to the next ones as we go. So this unit will be covering force, motion, and inertia. Now force is any influence that causes an object to undergo a change, either in movement, direction, or construction. Force is measured in units of newtons. It takes about 25 newtons of pressure to break an egg. So if you think about it, that really kind of puts it into perspective. When you hold an egg, that's about, when you break it, that's 25 newtons. So now force is also represented by the symbol F. F equals ma, or force, in other words, force equals mass times acceleration. Force, push or pull are real-world terms that represent force. So, for example, pushing a car is a real force, a real-world force. These people, it takes two people to push one car up the hill. Another pull is also a real-world term, so push and pull. A force can cause an object to change its speed and direction. As you can see pulling, I'm not sure if there are any buildings out there, but pull is an excellent example of force and motion. The whole object of the game is to knock one ball into the other and subsequently knock another one into the hole. So you can see that force causes an object to change its speed and direction. So you start out with the white cue ball and it knocks it into another colored ball, which then in turn knocks it into the hole. So the force of the first object changes its speed and direction of the second object. Now here's an interesting concept, balance force. The forces applied to an object are equal in both directions, canceling each other out. Therefore, we have a balanced object or balanced force. For example, we have an example here of tug of war. The person on the left and the person on the right are pulling the same, if they're pulling the same direction and the same amount of force on each side, I'll grab a little pointer. If this person on the left and the person on the right are pulling the same force, it'll be balanced and they won't go anywhere. However, if you notice carefully, over here, it looks like they have an extra hand. There's two people over here. Or maybe they just have 3 arms. We don't know. Either way, the person on the right could be unbalancing this this rope. Therefore, the rope would go that way. It would not be balanced. All right. Let's see. For example, an unbalanced force, the forces are applied to an object are not equal, causing the object to change. So like in the example here, we see the purple guys, there are only 3 of them. However, the green have 4. And yet, it looks like, oh, the line is here. I was thinking the line was over here, and the purple were down maybe. But nope, the green guys are definitely going to win this. Just because they have an extra person, therefore creating an unbalanced force. Great. Now, is this unbalanced or balanced? Interesting. So let's take a look and examine a few things. Are the forces balanced? Well, first let's identify what forces there are. Do you remember what a force is? Let's see. Let me just go back here to slide 2. I'll show you. 3, I mean. Any influence that causes an object to undergo a change, either in movement, direction, or construction. So force measured in newtons, like a push or pull. What objects in this slide are being pushed or pulled? Well, you can see there's the ground here. There's also a person running, and a force of their legs running on the hard concrete. So would this be balanced or unbalanced? Good. We'll think about that, and we'll move on to the next slide. All right, let's see. So we can see that it's unbalanced because the forces are not equal. They're obviously moving this way, and there's less force going that way. Okay, now let's look at gear ratios. In this page, you can see there's kind of an example of the different types of examples you'll see in the curriculum. Step 1 on here, it says, well, this is to get gear ratios. So the first step is to count the motor box, spur, and pinion gear teeth, then calculate their reduction ratio, spur divided by pinion equals the gear ratio. So you count the number of teeth on the spur gear, and then you count the number of teeth on the pinion. For the representation of this page, I will just do this for you. So we usually have a 15-tooth pinion. We'll say this is 15 teeth on the top. The pinion gear, however, what's the pinion gear? The pinion gear is 87 tooth. So we take 15 divided by 87, and that gives us 17 tooth, or 0.17. I'll just write this down. 17,241. All right, now step 2 is count the differential ring and pinion gear teeth, then calculate their reduction ratio. What's the pinion gear, or what's the ring gear? The third step is then to calculate the total driveline gear ratio, A times B equals C. The fourth step is then to calculate your wheel RPM and torque. So you take the motor speed and the gear ratio, which we just calculated, equals the RPM. So in this step, we'll take the differential pin and ring in. All right. Which I do not have, but that's all right. All right, I'll come back to this just in a moment. In this section, we have a comparative study. Now let's go back to here. Okay, now I'm good to go. Sorry, I had a bit of distraction there. So we'll take the differential ring gear, and we'll say, for the sake of this one, I don't have exact numbers. We'll call it a 15 to a 33. 15 divided by 33 is going to give us a 0.45. Repeated. So now we take 0.45 times the first number we got, which is 0.17241, And that's going to give us a 0.078. And that will give us our total driveline gear ratio. Next, we'll calculate the total RPM and torque, which is the motor speed, which is depending on what motor you have. Maybe you have a 5,000, or in our case, a 3,500. Doesn't really matter. We'll take the 5,000, for example. And that will give us our total RPM and torque. Great. So in this next section, we'll be checking our results in this last one. So in here, you'll validate the math that we just did in that last exercise by using the tachometer. And you can see you just simply put a piece of tape on here using the tachometer to measure the RPMs. And over here you use the torque meter to measure the torque of the robot. Lastly, we'll have the students install the motor gear reduction unit to reduce the speed but increase the torque. And also measure the torque on that and RPM to see how it changes. Alright, and then this is robot speed. Now we'll just cover inertia really briefly. Inertia is a property of matter by which it remains at rest or in uniform motion unless acted upon by some external force. Measure by how much force and energy is required to accelerate an object to a speed, or irreversibly, how much force is required to decelerate objects. The mass of a body determines momentum. P equals mv. Momentum equals mass times velocity. In a perfect world, force, the marble speeds up. Going uphill, it slows down. But on the same force, it just keeps going forward. A good example of inertia would be traveling in a vehicle, let's say a train. As the train starts to accelerate, the person is pulled backwards because of inertia. See? As the train starts to decelerate, a person is pulled forwards because of inertia. Disconnect one of the wires from the motor. Here's an example of how to test a simple test on here, which I will just cover very briefly. But you're basically going to set up this little setup here with the multimeter and then see how much voltage is on here. So you set up a group of people, you have the rover go down here, and you just read what it is, and it's going to go, the amps are going to go up, and they're going to level off like that. Alright, so that's pretty much all I have for today. If you have any additional questions, you can please contact me at this number, 509-252-5767, and you can also email me at tlines@mymindsi.com, and I'll get back to you as soon as I can. There we go. I think that's all that we have for today, and I will see you on Saturday as we discuss some questions or comments that you might have on the video. Thanks, and have a great day.